Hey, Honors Pre-Calculus, this is Miss Myers, and I just am going to do a short video on and talk about 4 different things. So these are questions. I'm getting some of the similar questions from you guys, and they're really good questions on some of the finer points on all the material that you've been working on. So I'm going to just talk a little bit about these 4 things: the derivative at a point versus the derivative as a function, the numerical derivative, upcoming notations for the derivative, and differentiability implying continuity. Okay, so if any of those things are things you're not sure you quite totally understand, watch this video. The notion of building a derivative and the slope of the curve has us at first fixing on a point. We look at nearby points and the slope of the secant line and move closer and closer and closer and closer until we build that derivative, right? So the definition of the derivative should be, for you guys, f prime of x is the limit as h goes to 0, f of x plus h minus f of x over h. All right, this is what I would use to calculate your derivative when I say use the definition and use the long way. But at the beginning of calculating a derivative, the book will fixate on a specific point because that's how we built this, right? So this references more the derivative as a function, which it is, but when we first build the derivative, we first need to define it before we can move to that notation. So let's just take a basic example and look at the difference. So let's just take f of x equals x cubed, and let's find the derivative at x equals 2, okay? So the first way you would do that is using that derivative. You would say f prime of 2, because we're at that very specific point, is the limit as h goes to 0, f of 2 plus h minus f of 2 all over h, okay? Versus writing it the more general way with a point x, okay? So we're going to look at the two of those. So versus, f prime of x being the limit as h goes to 0 of f of x plus h minus f of x over h, okay? So we're going to do it the first way, and then we're going to do it the second way and make sure all that is good and reconciles, okay? So at the very specific point 2, notice because we're at this point 2, when I take the limit, this should be a numerical answer, okay? This will be the slope of the tangent at the point 2. This, if I do it this way with an arbitrary x, I actually will end up with a formula for x. I still will never have any h's in it because once you take the limit as h goes to 0, the variable goes away. But you will then be able to apply that more general formula. It's a general formula for this whole curve to any point that you want, okay? So when I calculate derivatives, I like to do it this way because if somebody then asks me the slope of the tangent at 4 different points on the curve, I can quickly get it. Whereas this way, I only can get the slope at the one point, all right? So we're still going to write it out because you need to make sure that you that both ways are comfortable for you. So this is the limit as h goes to 0, and I have 2 plus h cubed because I'm sticking it into the function x cubed, minus f of 2 is 2 cubed or 8, all over h. And so let's keep expanding that. You get to use your little binomial theorem, 2 cubed, right, plus 2 squared, 2 to the first, and no 2's. This one will have 1 h coming, 2 h's, and then 3 h's. Okay, so plus, 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 minus the 8 over h. All right, now when you are using the definition of the derivative, if you did not already notice, you cannot calculate this limit as h goes to 0 with that h in the bottom. It cancels every single time if you're doing it correctly. So a really good check is to make sure you're not just running through the steps and skipping over things and canceling things willy-nilly, but making sure that you do get to the point where terms cancel in the top enough to leave you with everything else having h's in it so that you can cancel an h term, okay? So I'm continuing with number 1 and cleaning it up. So that's the limit as h goes to 0 of 8 plus 4h plus 2h squared plus h cubed minus 8. Notice the 8's cancel. And this is all over h. Give me one more step. Don't start just canceling that h. It's easier to not make mistakes this way. Give me one more step. 4, when I cancel those h's, plus 2h plus h squared. All right, now we have canceled the h in the bottom, so guess what? I can take that limit. That's a plug-in, right? And you get 4 for your answer. Okay. I didn't put my coefficients in. Sorry, guys. I knew that I was going to do it because I'm talking at the same time. The coefficients for the binomial theorem, right? 3, 3, 1, 3, 3, 1. 1, okay, so 3, 3, 1. So this is 12. So sorry, I do this every time I make a video. 6. Ooh, 12. Okay. So if we looked at the curve, x cubed, at x equals 2, that slope right there would be 12. Okay, let's go ahead and write the tangent line while we're here just to make sure that that part is okay with you guys. The point would be 2, 8, and we would say y minus 8 is 12, x minus 2 using the point slope form of a line. And you don't need to clean that up. Leave it just like that. Okay, it's a perfectly good equation of a line. All right. If you do this problem this way perfectly correctly, great, awesome. But now if I changed and gave you a part B to the problem and said, hey, give me the slope at 1, you would have to go back and do the whole darn thing again, which is annoying, right? So if we do it the second way, what we'll do is just do it for any x on that curve. And when we do, it's the same algebra, you're just going to have an x instead of numbers. We're going to still try to cancel the h so that we can take the limit, but we should expect then an answer that doesn't have h's in it, but it does possibly have x's in it, all right? This one up here didn't have anything but numbers because we were at the specific point getting that very specific slope. So let's do it really quickly. Don't drop your limit to the end, keep good notation. X plus h quantity cubed minus x cubed over h. And now I'm going to try the binomial theorem with the coefficients. Okay, minus the x cubed. That's all on the top. All right, sorry. I'll try to get a little bit neater here now. So notice the x cubes cancel. Those are the terms without the h's. So we have 3x squared h plus 3x h squared plus h cubed all over h. So a really good check for your derivatives. Did you get to that place where now you can cancel the h in each term? So it's 3x squared plus 3xh plus h squared. Now, once that h is canceled on the bottom, I can let h go to 0. It's a simple plug-in. That goes to 0, and I get 3x squared. So what you have told me is that for the function f of x equals x cubed, f prime of x must equal 3x squared, okay? Now, if I ask you the slope at 1, you can plug in 1 and you get 3. If I ask you the slope at 2, you get the same 12 that we got. If I ask you the slope at 3, you can give me the slope at any point on the curve, and that's how we move to the notion of you give me a point on the curve, I'll give you the slope. They're clearly getting bigger and bigger over there. And what we've done is now we can think of the derivative as a function because it's with every x input, I can give you a slope output, okay? So notice this derivative looks like a quadratic, okay? And you did some matching on the things before. All right, so let's talk about the numerical derivative next. The numerical derivative, sorry guys, is topic 2. Now, there's a definition in your book, but I'm going to go over just some main points to make sure that people got. So there was an exercise 38 having you play with things, but I'm going to use the absolute value for my explanation, and then you can go back and work 38. So the numerical derivative is defined as a symmetric difference quotient. So it's f of x plus h minus f of x minus h over 2h. Notice that's different than the definition of the derivative. The definition of the derivative doesn't have it symmetric. So you might think this is an equivalent form of a definition of the derivative. It's actually not. We have some problems with it. All right. It is what your calculator and computer systems use to estimate the derivative, okay? So instead of doing algebra and calculating limits that they can't do as easily, they can just number crunch really well, okay? So if I had a point like the last example around x equal 2 and I wanted that slope, the calculator would get 2 points really, really, really close to it, calculate that average rate of change, and use it for the slope. And it uses really small h's and is usually pretty darn good about those estimates, all right? The problem comes in something like the absolute value, okay? So we want to do the absolute value's derivative at 0. And I hope that you learned in your other videos that there is no derivative there. The slopes from the right are all 1. The slopes on the left are all -1. The right and the left-hand limits do not exist in that definition of the derivative, so the overall limit can't exist, so there's no derivative, right? All right, if I go to my calculator, and it's up because I just did it with Jenny, ddx, this is under Math 8 is the numerical derivative. So your book will call it NDER because different calculator systems use different notations, but numerical derivative. And basically you could tell it you want the derivative. This is part of our new notation I was going to talk to you about. You don't have to be an expert at it now, but as we move through the next chapter, you'll get better and better at it. But that's what we mean by taking the derivative of this function, the absolute value of x, and we want it at x equals 0. And notice when I do that on the calculator, it gives me an answer of 0. It doesn't understand that there's no derivative there, okay? Because what it's doing is zooming in really closely to your graph, taking 2 points on either side, but they have the same height, right? So their slope is 0. It's just getting an answer of 0. So the short of it is the numerical derivative is a great estimate for the derivative most of the time, but not all of the time by any means, okay? So be careful about that. The notations, you should mostly be using f of x and f prime of x for the derivative. Okay. Another notation, if we use y for our function notation, then we'll move to dy dx, and this looks different. So that's okay. That's supposed to be a little bit weird. These really come from two competing notations in calculus. This is much more Newton-based, where he actually uses a dot, but and physics-based. But this is Leibniz, the other founder, and this notation we really mathematicians prefer. It has a lot of great uses where we can treat things as a fraction even though they're not really. This is notation, it's not a fraction, but when we talk about really small quantities and such, we can use it as that, and it's very helpful. So this is another equivalent notation for the derivative, all right? So your calculator is saying d dx means take the derivative of this thing right here, okay? So that's a third notation that we'll be moving to, but you don't need to be an expert at it now, just getting there. The last thing I want to say in this sort of longer video is make sure that you understand differentiability implies continuity, but not the reverse. The converse of that statement is not true. There's a proof in your book. It's pretty short and sweet. You can just peruse it. Differentiability is a stronger statement. And so, differentiability, implies continuity. So if I know a point is differentiable, then I know it's automatically continuous there. All right, that's a very strong statement, and we do use it all the time. But continuity does not imply differentiability. What's your counterexample? And your counterexample is absolute value function. It's continuous, no problem, but you know it's not differentiable at that corner, okay? All right, I'm signing off now. Thanks for watching.